welcome everybody for this seminar of Marzia Parisi today. I'm very delighted that we have Marzia with us today. We postponed her talk many times, and now, despite the fact that she couldn't come in person, we are delighted to have her here giving a seminar remotely from California. So I just give a few words about the background of Marzia Parisi. Marzia Parisi works as a research scientist at NASA Jet Propulsion Laboratory. She's a member there of the Planetary Radar and Radio Science Group. Marzia graduated in 2015 from the University of Rome in the field of radio science, and later she went for postdocs at the Weizmann Institute of Science in Israel and also in Pasadena at NASA, where she is now a research scientist. Her research interests include gravity science, planetary interiors, and atmospheric radio occultations. She's involved in several missions, for example, the Cassini or Juno mission, or Bepi-Colombo mission to Mercury and Juice. So the screen is yours, Marzia. The word is yours.
Thank you, Caroline. Thank you for the introduction. Yes, so today I'm going to talk about what we learned about Jupiter's atmosphere and interiors during Juno Prime mission. And before I start into the presentation, as usual, I want to acknowledge all of my colleagues of the Juno science team and the interior working groups. And because the results that I will share, they are a group effort. So it's not a one-person show by any mean. Okay, so I prepared this slide a little bit about myself, but I think you covered most of it. Yes, as you said, I've been a Caltech JPL since 2016. And I work primarily on the Juno mission, but I also work on mission formulation, concepts for future space missions. And I also, when I was at the University of Rome, I had the pleasure of working also on the JUICE and Bepi-Colombo mission from the European Space Agency side. So these are a couple of my favorite pictures from work. So the first one is in Goldstone, California. Was like 10 years ago. That's a very big deep space antenna. This one is the 70 meters. And this is, you will see this is very instrumental to what I do. And the other one is in the dark room at JPL. So this is where we monitor the data coming down from the spacecraft. Also very important. Okay, so this is the outline of the seminar. I structured this one a little bit differently from what I do usually. After I give the introduction about the Juno mission and how gravity science experiments work, I decided to divide the seminar into 3 parts. So as Caroline said, I studied the gravity field of planets. So I divided it into the low degree gravity field, the high degree gravity field, and then the localized gravity disturbances. You will see after what I mean by all of this. So I don't know how many of you are familiar with the Juno mission, probably most of you, because Ravit works on the Juno mission as well, but just to give you a reminder, this is the spacecraft. There is a little human here for scale, so it's very big. The main feature are obviously the solar panels that cover a very large area of the spacecraft. And so the spacecraft has 8++1 science instruments, including our gravity science. So our gravity science instrument is composed of the Ka band translator, the X band deep space translator, and also the high gain antenna, this one here. The other instruments we have, so the microwave radiometer, and then we have dust detector, we have the spectrograph, an infrared camera, plasma wave instrument, and then also the magnetometer that you can see clearly here. So Juno arrived in 2016 at Jupiter after 5 years of cruise, and during the Prime mission, It was in a very elliptical and quasi-polar orbit, and the period was about 53 days, so almost 2 months. This means that the spacecraft actually spends a pretty good amount of time away from the planet, and then every 2 months it gets close to the planet, where most of the data is collected, including our gravity science data. So when it gets close to the planet, it actually gets pretty close. We're talking about 4,000 kilometers over the 1 bar surface of the planet. Okay, so with radio science experiments, we rely on deep space antennas. We use usually the 34 and 70 meters, and there are 3 NASA complexes, one in Goldstone, one in Madrid, and one in Australia, Canberra. So what happens is that we send radio links from the ground stations. We send them towards the spacecraft in X and Ka band. So just for information purposes, X band is around 8 gigahertz and Ka band is around 32 gigahertz. So we send these radio links up to the spacecraft coherently. The spacecraft receives these signals and then retransmits them back coherently. And the ground station then receives them again and records the received frequency. So the science instrument in our experiment is the Ka band translator. And very important is that the signals, as they traverse 5 astronomical units to get to Jupiter, they encounter several sources of noise, including the Earth's ionosphere and troposphere, but also interplanetary plasma, solar plasma, and in the case of Jupiter specifically, also the Io plasma torus, which is a very toroidal, very dense toroidal regions along the orbit of Io, which is one of the Galilean satellites. And this region is rich in ions and electrons, so obviously it distorts the radio signals. So in our analysis, we have to take into account all of these things. So, so this was the instrument, but also what is the physics of the experiment? It's pretty simple. So the spacecraft, as I said, it's in a quasi-polar orbit around Jupiter. So imagine that the spacecraft is coming from the North Pole and descending. So, and it's getting towards the closest approach to Jupiter. So as it does so, we have, let's say, a reference trajectory, which is the blue one, that and this is what we thought before, the actual closest approach. This is what we think the trajectory of the spacecraft will be. However, the actual trajectory of the spacecraft, which is the orange one, it will be for the most part like the reference one, but there will be slight perturbances. And this is because we can't model perfectly all the gravitational, but also non-gravitational accelerations before we get there. We need to be there to understand exactly what's going on. So because these two will differ, then also there will be an effect. Also the frequency that of the radio signal that is received at the ground station will be slightly different than the reference one. And this is because it's now carrying the Doppler effect due to these slight perturbations to its trajectory. And these differences between the reference and the actual observations are very important to us, because this is what allows us to correct the gravity field of the planet and also other non-gravitational effects. So as you see here, as I said, it's pretty simple. The Doppler shift is proportional to the variations in the line of sight velocity of the spacecraft. So basically, we measure the Doppler shift at the ground station. Hence, we measure the velocity perturbations. Okay, so but what can we do with knowing the gravity field of the planet? So here are just a few questions. There are many things that you can do, but I focus primarily on the atmosphere. So Jupiter is famous for being a very colorful, bright, and you see the red spot here in this picture, but you also see the bands, the zones and belts of the atmosphere. So one question that scientists were very interested in since always is what's going on below what we actually see, so below the visible cloud tops. And how deep are these winds? Because you can see the differential rotation of the atmosphere, but how deep are these winds that we see so clearly? And also, what is the mass of the denser core, if there is any? And all of this information together with others that I didn't mention here, they help us learning about planetary formation. So this one, okay, this is a plot that I borrowed for my postdoc advisor. So he plays golf, I don't, but I like this image because it shows you different possible interior structures of these golf balls. So the message here is that we can measure the external gravitational potential of the planet with pretty good accuracy. And I will show you how we did this with Juno. However, the multiple, infinite, I would say, interior structures can give you the same external expression of the gravitational field. Obviously, there are other physical considerations that we can make that help us choose, let's say, a set of interior models that we think are more physical and and there's a higher probability that this is what's happening. But just by looking at the gravity field of the planet, there is no way to determine a unique interior. Okay, so the gravity field, how do we, what do I mean by measuring the gravity field? So the gravity field of a planet, we have the monopole term, which is the one that we're used to. This is the point mass term or spherical symmetry term. And this is what we know from school and from Newtonian gravity. However, the mass distribution of the planet is never perfectly spherically symmetric. And we have, for example, the first term that comes to mind to most people is the oblateness, or J2, and this measures the pole flattening of the planet. So we have this on Earth as well, right? Because we have an equatorial bulge and the polar radius is smaller than the equatorial one. There's also the J3, which we call pear shape. This measures the asymmetry between the northern hemisphere and the southern hemisphere. And as well, on Earth, we have this because there is an imbalance of mass between the northern and southern hemispheres. And so on, we have J4, J5, J6, J7, J8, and up to as many as you want. And all of these, any of these terms measures a different deviation from the spherical symmetry. In general, the ones that have even indexes, so in this case, the ones with the yellow circles, they are symmetrical with respect to the equator, as you can see. So for gaseous planets like Jupiter, so Jupiter is a hot ball of gas that is spinning very fast. Remember that the rotation rate of Jupiter is faster than the one on Earth, so it's pretty fast. So obviously we expect the planet, which is made of gas mostly, to being deformed in a way that is coherent with centrifugal force. So obviously this has to be axially symmetric, but also symmetrical with respect to the equator. And it follows basically the profile of the angular velocity. And on the other hand, we also have the odd harmonics, and these ones are the opposite. They are asymmetric with respect to the equator. So in this case, they cannot be related to uniform rotation, but they have to be related to, in the case of gaseous planets, most likely to the atmosphere, to the differential rotation. So going forward, remember we have the even harmonics, and they relate to uniform rotation with the magnetic field of the planet. And then we have the odd harmonics, and they relate to the differential rotation or winds. So after the first few perijobs of Juno, so just to give you a reference, at the end of the prime mission, we had done a few perijobs, more than a little bit over 30, and now we are on orbit 42. We are in the extended mission, so I'm not going to talk about the extended mission. And yes, so as I said, every 53 days we were approaching the planet. So after the first few, we measured with very good accuracy the gravity field of Jupiter up to, I would say, J9. So the first 8 harmonics. And this plot is from a publication from 2018, and it shows you basically the measured values of the J's, and also the formal uncertainty at the 3 sigma level. So as you can see here, you have the even harmonics. This is what I talked about regarding the uniform rotation. So really not a surprise here. It follows the profile of a uniform rotation. What you would expect, it's a straight line on in the log scale, and this is what we expect from planet that is spinning very fast. The big surprise was, at least for people that are studying the atmosphere, was the detection of the odd harmonics, and this was the first detection of an odd gravity field for a gaseous planet. So we had that before with terrestrial planets, but this was the first time for a gas giant. And you can see they very clearly are above the sensitivity level. So we have a very solid detection of J3, 5, 7, and 9. And this was exciting because we knew that this was related to the winds. So because the winds, they move mass around. So the more mass you move around, so the deeper the winds, the more mass they would move around, and then the strongest would be the gravitational signal. So in this plot on the left, you see so this is the odd signal that I showed in this slide. So imagine these 4 J's plus all of the J's that are above J10. So basically the whole gravitational signal, but removing the biggest terms, which are J2, 4, 6, and 8. And we plotted this as a function of latitude, and you can see the error bars here. So as you would expect, you know the surface gravity pretty well, where you get, around the closest approach, and then the formal uncertainties is increasing towards the poles. And this is because Juno, when it gets to the closest to the planet, the latitude that these perijobs occur are concentrated in a latitudinal band, which is between 5 degrees and I think by the end of prime mission around 30 degrees. So they are concentrated in the first part, in the lower latitudes of the northern hemisphere, and then when you go closer to the poles, the formal uncertainties obviously are increasing. But the interesting thing here is that on the right we plotted the zonal wind velocity profile in meters per second, and you can see that these two plots correlate pretty well, right? You see correlation in the lobes. So this was a very good indication that indeed the odd gravity field is related to the winds. So this plot is from a companion publications to the one that I just took the plots from, and this is by Kaspi et al. So what they did to determine the depth of the zonal winds is so they constructed a model of Jupiter's atmosphere by using the thermal wind equation and basically solving it numerically. So then if you have a model of the atmosphere, you can predict what the density perturbations are, and then you can predict what the gravity field will be and what the J's will be. So this is what they did in the colored lines that you see here. And you have this for the first 4 odd harmonics, which are the ones that we got from Juno. The dashed lines of and they are coupled in color, they are the observations, the actual observations. So if you look at where the model intersects the observations, you will see that they all intersect in a range of depth that is between 1,000 and 3,000 kilometers. So by doing these analyses, they were able to conclude that the winds are a few thousand kilometers deep. And well, JPL made this animation. I think it explains pretty well what we mean by a few thousand kilometers deep. So basically, the winds, imagine that the surface winds are propagated internally, so within Jupiter's interior, along coaxial cylinders. But then at a certain depth, these winds are truncated. So you have the interior of the planet, the most interior part that it's actually rotating uniformly. And then you have differential rotation that goes as deep as 3,000 kilometers. Okay, so that was the part about the low degree gravity field. And by low degree, I guess you got it from my explanation. We mean a large scale. So the lowest the degree, the largest the scale, the spatial scale. So I don't know if you want to take all the questions at the end, or but if you have any questions, feel free to interrupt me. I know that it can be a lot altogether, so feel free. Okay, so that was the, as I said, that was the measurement of the low degree. So what about the high degree gravity field? And what we mean by that is the smaller spatial scales, so above J10. So as I said, the geometry of the orbit of Juno is such that it gets close to the planet only for a few hours every 53 days. And as I already mentioned, all the perigeos were constrained within a very specific latitudinal range. And in the case of this publication, this is only up to orbit number 17. So the latitudes are within 5 and 18 degrees. So it's these solid lines here. Now we're up to 35 degrees, but still they are constrained in the northern hemisphere. So the reality is that we have very, very accurate gravity measurements within the dashed line. So I would say between 15 degrees south and 45 degrees north. As we go over the poles, the spacecraft gets farther away, and then the accuracy of our measurements are limited because, as you know, gravity is strongest when you're close to the planet, and then as you go far away, it decays exponentially with an exponent that is it's a linear with the degree. So the highest the degree, the fastest the gravity is decaying. So if you remember the slide about the spherical harmonics, what is the issue? The issue is that they are instead defined over the whole sphere. So from latitude -90 to 90. But here you have very good accuracy in a latitudinal band. So what happens is that for the low degree, they are so strong, these effects are so strong that it doesn't really matter. The spacecraft is still able to pick up the signal, even so far away. But for high degrees, because they decay fastest with the degree increasing, then the correlations are very high. If you use spherical harmonics, the signal is reduced. So what happens is that for all the J's above J10, the observations lie actually below the sensitivity level, so below the 3 sigma curve. But this is also a different way to see it. You can look at the surface gravity instead, and this is exactly what I showed earlier, just with more data. We know the surface gravity of Jupiter very, 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 very well, to better than 1 milligal in this latitudinal band that is between 15 degrees south and 45 degrees north. However, as we go towards the poles, then this uncertainty increases. There is a way, however, to kind of overcome this issue. There are actually many ways. This is only one of the ways. But instead of using spherical harmonics that you remember, they go from, they are basically periodical functions that they go from the South Pole to the North Pole. We decided to, okay, let's try and use a different mathematical basis, because no one prescribes that you have to use spherical harmonics, even though they are the more traditional way of looking at the gravity field. So in this case, in this publication, we computed what we call Slepian, what are called Slepian functions. And Slepian functions are linear combinations of spherical harmonics, but they are combined and maximize and optimized in a way that if you see, you select a latitudinal range, let's say, as I said, minus 15 and plus 45, and then you can prescribe that these functions will take values that are different from 0 only within this latitudinal range, and outside they can be 0. So this is exactly what you see here. And this is because we thought, okay, we have more data concentrated here. We don't have much data at the poles. So let's see if we can get the high degree gravity field by using this approach instead. So now, instead of measuring the spherical harmonics, we're measuring the Slepian function coefficients. And the Slepian function, they basically behave exactly like spherical harmonics. Remember what I said, that the deeper the winds, the more mass involved in the circulation, and then the strongest the gravity signal, and then the largest the J's, or whatever coefficient you use to describe your gravity field. So they behave exactly the same. So in this case, you have winds, different wind profiles that they go. The shallowest ones are 100 kilometers here, and then they go up to 7,000 kilometers. And you see the coefficients are just increasing in amplitude. Okay, so in this paper, we compared the more traditional spherical harmonic approach to the Slepian approach. And let's focus on the left part of both plots. So before J10, so you can see that if you look only at the low degree gravity field, then you have a measurement that is just as good for spherical harmonics and for this hybrid approach that we use with Slepian functions. So not much to say there. However, the big difference is in the high degree gravity field, because as I showed you earlier, with the spherical harmonics, they're all below the uncertainty line. But for the Slepians, because we concentrated these functions where we actually have the data, then we are able to pull these coefficients out of the uncertainty line. And this is due in part because you have lower correlations just because the functions are optimized. So in this case, what we did, I'm sorry, the colors are not the best, but basically we compared again the model obtained by solving the thermal wind equation. And this model assumed a depth of 3,000 kilometers. So we used the knowledge from the low degree gravity field, and we projected this gravity signal into Slepian functions. And then we wanted to see how they correlate with the actual measurements. So the squares here that are kind of green, these are the model, and the other ones are the observations. So we were surprised to see that they most definitely match when it comes to the sign of the coefficient for the most part, and then to some extent also the magnitude. We were able to measure the high degree gravity field. Now, obviously, this is not the only way to do that. It's possible to do it in other ways. For example, put constraints at the poles, or using an entirely different mathematical basis. But this is just to show you that you can play. You have the gravity signal, you measure it. You can play with the mathematical functions to understand what works best for your situation. So for Juno, for example, it's not, this is a mission to the outer solar system, so it takes a lot of fuel to operate the spacecraft. And you know, you have an amount of fuel that you begin with at the beginning of mission, and then once you are in the outer solar system, it's not like you can refuel or anything. So you have to optimize your fuel consumption. So it's not very it's very common for the outer solar system missions to have this kind of orbit. It's very challenging to put a spacecraft in a circular polar orbit around a gas giant, you know, for obvious reasons. I'm not a mission design person, but you know, the gravity of Jupiter is huge, of course. So it's very challenging to just compensate for the dynamics. And for example, also the Cassini mission, it had this kind of orbit at the end for the grand finale. It was very similar. It was with a different period, but it was, again, getting very close to the planet for a short amount of time and then far away and then again. So these are very typical orbits. So of course, you know, you have to adapt your tools to the kind of orbit that you have and not the other way around. I mean, it would be optimal also to do the other way around, but it's not always possible. So yeah, just to show you.
Mm-hmm.
Yes.
I have a very quick question. To these plots, there are filled circles and squares.
Yes.
What do they represent differently than the non-filled?
Oh, sorry. Yes. So the filled ones are positive, and then sorry, I should have said the empty one are negative. So these ones, this is the low degree gravity field, and you have these ones. The green ones are the model coming from thermal wind, the solution of the thermal wind equation, and then you have the ones that are, let's say, white, and they represent the observations. So this is you know, observation against model, but we talked about this right before about the low degree.
Yes.
Actually, the other plot, let's say this plot shows it much better. But then the interesting part is this part, and you have again the model that predicts the Slepian coefficients, and then you have the actual observations, which are the white ones. So you see that the signs, they correspond pretty well. I think there is one that doesn't match, but you know, for the most part they match. And then the
S9, yes,
exactly. And then for the magnitude, they do match for the most part. But remember, this is not an optimization, so we're not trying to determine the depth with an you know, optimization algorithm. We're just comparing the model to our observations. So it's basically what it says is that, okay, we already knew that the large scale winds were 3,000 kilometers deep. What about, you know, the shorter scales, the smaller features that you see? What about them? Well, you know, this shows that for the most part, they are also in the ballpark of a few thousand kilometers. So they're not much, you know, shallower and not much deeper than the large scale winds. Okay, but actually now we look at completely different thing. So everything that we talked about now, until now is zonal, so axially symmetric. And now we want to look at the very localized gravity signal of you know, Jupiter's atmosphere. So here in particular, we focus on the Great Red Spot. So Great Red Spot, you know, very famous, largest and you know, most enduring storm in the solar system. And we know that we have observed it for at least 2 centuries. You know, maybe since the 17th century. So the Great Red Spot, so we know, even before Juno, we knew a lot about the winds surrounding the red spot, which are these anticyclonic winds. However, because they can be observed also from Earth. However, we didn't know much about what was going on below. So, you know, we know that the Great Red Spot is red. It has this very typical color. The winds were studied, but we didn't know how deep it was. And this puzzled you know, people in our community, because some said, okay, you know, it's a very shallow feature. It's confined to the weather layer. Other people said no, but it's lasting so long, so it has to have deep roots. Otherwise, if it was so shallow, it would have, you know, already disappeared. And so with Juno, we had the first opportunity in a long time to closely observe the storm once in 2017. And this flyby was dedicated to microwave radiometer observations, which at the end of the presentation, I will tell you why it's important. And then again, twice in 2019. And this time, both flybys were dedicated to gravity instruments. And then two companion papers were published, one on the microwave radiometer results and one on the gravity results. So obviously I will focus on the latter one in this presentation because this is what I do. Okay, so the two gravity flybys, they were labeled PJ 18 and 21 because very simply they happened on orbit number 18 and 21. So as you see, these are like relative plots, doesn't take into, this is the relative position of the spacecraft compared to the red spot, taking into account the rotation, because you know that the red spot drifts by a few degrees. And then also, you know that the planet rotates below. So taking into account all of these relative motions, this is what you end up with when you compare the spacecraft trajectory with the position of the red spot. So PJ18, it was actually closer to the vortex. We flew 13,000 kilometers, over the red spot, but it had a larger longitudinal offset, about 11 degrees. And then PJ21 was the opposite. It's farther away, about 20,000 kilometers, but it flew right above the red spot. And you know that for gravity, it's very, very important to be close by. So we had a combination of factors here. One was closer, but the other one was right above. Okay, so here I'm gonna play a video. Well, it's more like sound. So we made, it's a rendition, it's a sonification of the Doppler effect that we recorded when flying over the Great Red Spot. So I remember how I said that the Juno spacecraft, you have a reference trajectory, but then you have an actual trajectory that is perturbed because you have this very slight perturbations in the gravity field. So I already removed the largest effects from the J2, the J4, and even the other zonal wind. So I removed all of the effects that I knew about, and then with the objective of leaving only the Doppler shift that is due to the Great Red Spot. Of course, this is very challenging, but we wanted to show what is the kind of measurements that you can do with this instrument. So basically, you will see a sonification. You will hear the sound that comes from the Doppler shift that we recorded when flying over the red spot. So let's see if. So yeah, basically you heard that those ups and downs. So those ups and downs are, the slight perturbations when we flew over the vortex. So, and oops, how do I go? Okay, so same as the zonal winds, we're interested in the depth, right? And we can get the depth of the vortex by measuring the gravity signal. So in this slide, I go into more details of what you heard in the slide before. So this is in the upper left plot. You see that the white line is exactly what you heard earlier. So this is the observation. This is the Doppler measurement, and then the colored lines, they are again models of the Great Red Spot, assuming different depths. So in this case, we're not talking few thousand kilometers, we are talking few hundred. So you have 200, 400, 600. And you see that actually the shape of the model matches pretty well the observations for a Great Red Spot that is a few hundred kilometers deep. And this was for PJ18. So this was the first flyby. So this was the close one. For PJ21, the match of the shape is not as good, but you have a pretty good match of the lingering delta V that you have after flying over the Great Red Spot. And basically, this is very typical of flying above a mass concentration, because basically, if you are familiar with the, also, let's say, gravity assist, you fly by a massive body, and then you get like a kick. You get a delta V out of it. This is how gravity assists work. And I would say the principle is the same. You fly over a mass concentration, and then you get a delta V out of it. So the spacecraft is either increasing or decreasing the line of sight velocity. So in this case, in the case of PJ21, there is a pretty good match of the predicted delta V after flying over the Great Red Spot and the measurement. So we decided then to look at the delta V for all the perigeos. Okay, and this is this plot here on the right. So this one is I will try to be as clear as possible. So you have this Doppler signal, right? And the Doppler signal is pretty, once you have modeled all the effects well, then it's supposed to have a zero mean, okay? So what we did was we took the mean of the Doppler, which is proportional to the delta V, so the velocity increase. And then we did this for all of the gravity perigeos. So not only PJ18 and 21, for all of the gravity perigeos. So the blue ones are all the non-GRS perigeos. So these are the flybys that were not over the vortex at all. Like they were very, very far away. So in this case, we did the mean of the Doppler before and after the the 20 degrees south, which is the latitude of the Great Red Spot. And we noticed that the mean is zero, basically, because this is the sensitivity level, the dashed line, and these are all the delta V's before and after crossing the 20 degrees south. Now for the PJ18 and 21, this is different. So if you take the mean before crossing the GRS, that is also zero, zero, below the sensitivity line, which you see here. But afterwards, you clearly get two outliers. So you get a delta V, which means you get a delta V after flying over the vortex. And this means detection of the gravitational signal. And another thing that we looked at was, again, the color code is the same. We looked at the correlation between the curve for 300 kilometers coming from the model and the actual observations. And we saw that the correlations are very small, below 20% for non-GRS overflights, and then they are as high as 60% for the GRS overflight. So again, detection of a very faint, but it's there, gravity signal. Okay, but how did we actually model the Great Red Spot, right? Because we're making all these predictions of the signal that we are supposed to see. So how do we make this? So again, this is solving the thermal wind equation. This plot on the left is showing the density perturbations. So we see that the anticyclonic winds of the red spot, they create a positive density anomaly closer to the surface, and then a negative one at depth. And to first degree, these two masses are equal but opposite, so their sum is zero. So basically, and this is because you need to keep the mass of the planet constant. Obviously, you know what's the mass of the planet. So the fact that it's zero, it's basically conservation of mass. However, so you could say, okay, so if they are equal but opposite, don't they cancel out? Well, imagine though that the spacecraft is flying above the surface, right? So it will sense, yes, they are equal but opposite, but the spacecraft flies closer to the positive mass. So there will be actually a residual signal from the Great Red Spot. The right plot instead, it's taking these density perturbations and then it's projecting them onto the surface gravity. So this is basically the gravity perturbations that you will see over an equipotential surface. And in this case, you have a north-south dipole, you have a negative gravity anomaly at northern latitudes and a positive one at southern latitudes. So we basically used two methods to get the depth of the Great Red Spot. In the first method, which we call MASCON, because MASCON is mass concentration, we measure directly the mass of the Great Red Spot coming from these density anomalies. Okay, so we have the yellow line is the model, and it's the mass, the expected mass from the Great Red Spot as a function of the depth. And this is exactly the same principle as the zonal winds. As the depth increases, the mass involved in the circulation increases. And the dashed line is instead the observation with the our measurement with the formal uncertainty, with the error bar. And then you see that they intersect around 300 kilometers. And then, at the 3 sigma level, we can say that the Great Red Spot is not deeper than 500 kilometers. The other method measures instead directly the surface gravity. And in this case, I don't have the time to go into details, but what we did was, what my colleagues did was to construct a Slepian function. So remember from earlier, that has this exact shape. It's a dipole north-south. And then you measure the coefficient of this Slepian function, just like we did for the high degree gravity field. And again, you have the model, you have the magnitude of the gravity signal that increases with depth. And then you have your measurement, which again intersects at 300 kilometers. And you have the 3 sigma level that says that the Great Red Spot is not deeper than 500. Okay, so in conclusion, this is an animation that we made for the press conference that we had. So the GRS, so we measure the GRS to be 300 kilometers deep at the 1 sigma level. However, if you consider the 3 sigma level, we can say that the Great Red Spot is contained within the first 500 kilometers of the atmosphere. So this is much deeper actually than some of the models predicted, even if the aspect ratio is still very small, it's alpha%. And so this gives the Great Red Spot a pancake-like shape. But it's much deeper, for example, of the visible clouds and the water condensation level at 80 kilometers. And then to give a reference, the ISS is orbiting 300 kilometers above the surface of the Earth. So, you would have the Great Red Spot going from basically the sea level until the International Space Station, to give a reference. Okay, so what's next? This presentation was about the prime mission. Obviously, these are not all the results of the gravity experiments. There are people like Ravit and others that they do interior modeling, so they look actually even deeper than the atmosphere, and planet formation and so on. So these are by no means all the results, but we've been extended until 2025, and one thing that it's very exciting is that in the extended mission we have flybys of the moons. So we already had one of Ganymede, and we will have one of Europa very soon. So this is an exciting new aspect of the mission for the next years to come. And again, I want to thank the whole Juno Science team, in particular the interiors and also atmospheric working groups. Yeah, thank you for your attention, and I will take questions.
Thanks so much, Marzia.
How am I doing? How did I do with time?
That's all fine. Yeah, we have enough time for questions. Perfect. Are there any questions? I will. So far, I wanted to. It's more like a comment. I really like the approach of using the wavelet functions, these Slepian functions.
Oh, okay.
That's a very, it's a very elegant move to have functions that are concentrated where your data is sensitive to. Yeah. Yeah.
So we actually, they are used a lot for Earth, because sometimes when you have when a spacecraft, you have the orbital inclination, it means that basically the latitudes that you get closest to are limited to the maximum is the inclination of your orbit. This is like a hard rule. So sometimes you have like what they call polar gaps. They don't have data at the poles. And then this is making your spherical harmonic solution it can be unstable, especially if you go to high degrees. So it's used a lot for that. Or if you, for example, when you're looking at very localized features like the Great Red Spot on Jupiter, but even let's say on Earth even more, because we have much more data. So you can look really, I don't know if you're familiar with the GRACE and GRACE follow-on missions, but they look really, really, detail the evolution of the gravity field of the Earth. So you can use Slepian functions to look at very localized, and then spherical harmonics are also not very good, right? Because they're global functions. So they're excellent to look at the large scale, but also like global gravity field. They're very good, but if you want to look at something precise, it's like it's like the Fourier theorem. Like the smaller, if you're looking at very localized signal, then obviously periodical functions are you need a lot to construct to really represent that concentrated signal. But instead, if you use an already concentrated function, then you need fewer. And then in gravity science, the fewer coefficients you estimate, the better, because then your uncertainties are smaller. If you need thousands of coefficients, but you have very limited data, obviously your uncertainties will be. So ideally you want to use the smallest set of parameters to estimate the field.
Exactly. Yeah, that's very nice. I like this very much. Are there questions from the audience? I just saw Ravid, your video is on. Do you have a question? No,
I don't have a question.
Okay.
She knows my work pretty well.
That's true. That's true. Well, and maybe a question, when you said about non-gravitational accelerations, are these the winds essentially, or is there something else?
Oh, like atmospheric drag?
Okay.
Well, so yes and no. The Juno orbit was designed so that it's not affected by the atmosphere in a more mechanical. Well, it is affected in a gravitational sense, but not in a mechanical sense. Of particles actually hitting you and slowing you down like atmospheric drag. So, but yeah, I mean, I remember I worked on Cassini on Enceladus, which is a small moon, and there, you had actually the atmospheric drag from the plumes, because we flew right through the plumes. So in that case, you have to consider the atmospheric drag, and then you have to model an effect that is non-gravitational. But you have other things like, for example, the albedo of the planet, the thermal emissions. You have large solar panels, so you have large surfaces. So these are all effects that you need to consider, right?
Wow. So these effects are accounted for.
Yes.
For this, yeah. Wow.
In our code, yeah. So I don't know if I forgot to mention probably, but before, if you want to know the gravity field, you have to model the trajectory of the spacecraft rather well. And obviously, you need to know the gravity field of the planet, but also everything else that is non-gravitational. You need to model pretty well, because they are pretty, everybody would think, okay, compared to the monopole term of Jupiter, which is huge, right? These are very small effects, but with our instrument, we have sensitivities on the velocity of the spacecraft that are a few microns per second. So you can know the velocity of the spacecraft to a few microns per second. So that's very, very precise. So even this, the smallest effect, we can see that's why we were able to see the signal of the red spot, which is very small. It's very small. So yeah, you really need to do a good job with that.
That's really amazing. If nobody else has a question, I have another one. When you showed these Slepian functions for different sensitivities in depth, I guess there was at the level 5, you always had a smaller signal.
Yeah.
And I was wondering, is there like a physical explanation? Is there?
So the only thing that I can think of is, you know, you look at the fifth Slepian function, and it has this shape. So it has to mean that basically the signal from the winds, when you project it onto this function, it has the smallest signal. So basically it means that the surface gravity coming from the winds matches this shape the least. This is the explanation. But yeah, it is very consistent. Like it's always, which is good. I think it's a sanity check that your model is working.
Okay.
Right?
As these winds are connected at these different depths. Or why do you say it's?
Yes, because you are projecting the same surface winds, right? You're not changing the surface winds, you're just changing the depth. So yeah, it means that, you know, they are all you know, in the same family, except they are truncated at different depths. Yes.
Yeah. Okay. Thank you.
Yeah.
Any other questions? Your talk was so clear, so it's
exactly.
I guess that's why there are so few questions. But this was an excellent talk. I really enjoyed it. Thanks so much.
Thank
so
you.
if there are no other questions, I think we are also just about time. It's 5 o'clock. So thanks so much for joining us so early, for giving a seminar. This is really awesome that you took the time. And if you can come in person, I think you're very welcome to come to Zurich.
I plan to. Yeah, I plan to.
Perfect. Thanks so much.
Thank you.
And I wish everybody a good weekend.